Well, let's continue on here. We were looking at vectors, and I told you about the IJK notation, and we'll be using that all semester. The IJK notation, where our I is x, our j is y, and our k is our z vector. So for example, if you have this motion, you move 10 meters to the right, 12 meters backwards, and 2 meters up. What would be your displacement in vector notation? How would I represent that in vector notation? First of all, which is the x direction, or what is our magnitude in the x direction, or displacement? That's our 10 meters, so this is our x. And our y is what, 12 or 2? Well, it sort of depends how you define it, but if we look at our x, y, and z axis like this, typically up and down is in the y direction. So our y would be the 2 meters, and then our z would be the 12 meters. So if I wanted to write this, I would have 10I, 2j, and 12z. Or excuse me, 12k in the z direction. I didn't put any signs in there. What would be my signs? For the 10, positive or negative? Positive, right, because we use this right-handed coordinate system where right is positive. Our y is going to be plus or minus, plus, and our 12, our k, is going to be plus or minus, negative, right, because here coming out of the board, that would be, forwards, as you would say, is positive, and then this is the negative k direction. So that's how we'd write that vector in terms of um, IJK notation. We can also write our velocity and acceleration. Now remember, we define velocity as dx dt, right? That's our definition for velocity. It's the derivative of the position function. And so we can write our velocity function in terms of IJK like this. It was going to be dx dt in the I direction plus dy dt in the j direction plus dz dt in the k direction. That's really just expanding that definition of our velocity into the 3 dimensions. And then also we can do the same for acceleration. Remember, our basic definition for acceleration was dv dt. It's the first derivative of the velocity function or the second derivative of the position function, which we've already done. And so we can express this as the derivative of v dt. We're looking at the x component of that velocity as it changes with time in the I direction plus dvy dt in the j direction, dvz dt in the k direction. It's just based on our definition. We're just expanding it out in vector notation where we have velocities in all 3 directions, or rather we have an object that's traveling in a certain direction that's on neither the x, y, or z axis. So the velocity is going to be the sum of those 3 components, the 3 components of that particular vector. Yeah? Okay. We'll see this. It'll come into play in some of our problems. Let's see. What was that? Oh, I'm sorry. That's where I was going to write that. Likewise, we can also define our average velocity and acceleration in terms of this. So if this is del r, if our average velocity is del r dt, we can express this in terms of our x, y, and z components. We're not going to see this, but I just sort of want to throw it out there. So it would be like del x, del t in the I direction plus del y, del t in the j direction, and then also in the z direction. But we're not going to see average velocity for the rest of your life. But some of you might see it in some other classes, but we're not going to see it in this class again. Likewise, we're not going to see average acceleration again, but you can imagine that you can split it up into your x and y components like this. In the j direction, and then also in the k direction. But again, you're never going to see this again in this class. So we're not going to deal with average velocity or acceleration. It was really just important to help define what instantaneous velocity is. Because remember when we defined instantaneous velocity, we defined it as the limit of what? Do you remember? So we said that limit as delta t approaches 0 of what gives us instantaneous velocity. You remember? It was the del x over del t, right? And we let delta t get really, really small, and then that defined our instantaneous velocity. So anyway, that's what this is right here, right? We are just using the average velocity to define our instantaneous velocity. Rainy day at 7:30, right? Is that the problem? Oh, I'll look a little happy to be here. All right, let's do some vectors. This is going to come up a lot in Chapter 4, and on this next test, you might just have a straight-up vector problem. I give you two vectors, and you have to do the sum of those two vectors. Let's see, have we done one like this before? We have not. This is our first one. So let's say that I have two vectors, A and B, and I just want to add them up. Now, most of you are in the lab, right? Have y'all had this lab yet? Yeah, so you did this in lab this week. I know that not all of you are in lab, so let's step through this, or some of you have it this afternoon. I have two vectors, a vector A and a vector B. I always like to draw them out first. I want to know the vector R equals A plus B. So I'm just going to sketch it out. I find this to be helpful. I'll draw vector A in blue. Vector A looks like this. It's 1 meter long, and it's 45 degrees from the x-axis. And then vector B is 2 meters long and 60 degrees from the x-axis. So I'm going to draw it tip to tail. I'm going to draw it twice as long. So that's vector B. This is vector A and vector B. Remember how I draw them graphically, that tip to tail. I draw the first vector, and then I pick up with the second vector. And then if I want to know the sum of those two vectors, I start here and draw here, or do I start here and draw here? The first one or the second one? All right, the second one. I start at the beginning of A and draw to the end of B. Because if you're a little guy walking along this path, that's where you start and that's where you finish. Right? If you think about it in terms of displacement. Now, the sum then of these two vectors, starting at A and ending at B. So this is going to be the vector R. All right. Sketching that out helps you to know a couple of things about the vector R. First of all, the big thing is when you find the direction of vector R better be bigger than 45 degrees, because I can see in this figure that it is bigger than 45. Um, I can also tell the magnitude is definitely bigger than 2 meters, probably more like 3 meters, just looking at the length of that vector and comparing it to the vector B and A. I want to show you graphically sort of what's going on here, and then I'll write it out in mathematical terms. But what we're looking at are two vectors, A and B. Both of these have x components. So the vector A has an x component that's right here. We've already seen how to find that x component. It's just the magnitude of A times what? It's either sine or cosine. Which is it for the x component? It's the cosine. Remember, that's based on the definition of cosine, but you sort of just want to have a knee-jerk thing where, oh, the x component is the cosine times the magnitude of the vector. You want to be able to do that quickly, assuming, of course, that the angle is measured from which axis? From the x-axis. And I recommend that you just always measure your angle from the x-axis. We'll see some cases in Chapter 4 where that won't be obvious, but you'll get the hang of it. All right, so that's the x component of A. We also have an x component of B. This is bx. And then I can also show you that we have an x component of R. If I bring this down like this, my x component of R looks like that. Now notice, I'll write this out a little bit later. I'm just going to sketch it in right here, that Rx is equal to AX plus BX. The x component of R is the sum of the x components of A and B. And then we can do a similar thing for the y components. I have a y component of A right here. I have a y component of B. Remember, it's just like the projection onto that y-axis. And then similarly, I have a y component of R. So this is RY, and then I have AY and BY. So I can say then down here that RY is equal to AY plus BY. Once I find the X and Y components of R, this is RX. I'll translate my RY over. This is RY. Then I can find that vector R. So that's sort of how we would do that graphically. Uh, but the math is pretty simple, so let's step through that. I sort of outlined it here. The first thing that we want to do is to find the components. So if I want to find AX, that's going to be A cosine theta. AY will be A sine theta. See, I can put in the numbers that we have for this. 1 cosine of 45, 1 sine of 45. Now the sine and the cosine of 45 are equal, so both of these are equal to 0.71 meters. And then for vector B, similar B cosine theta, B sine theta. It was 2 meters. And then I have cosine of 60, right? Wasn't it 60? Of course, the cosine of 60 is a half, so that's equal to 1 meter. And the sine of 60 is like 0.86, so this is 1.7 meters. Any pre-med students in here? We have a few, right? All right, remember MCAT, no math on the MCAT, so it really would help you now to sort of remember like the particular trig functions that don't have, did I say no math on the MCAT? No, no calculators on the MCAT. So it would behoove you to sort of practice taking exams and stuff without using a calculator. And part of that's just memorizing what the trig functions are. 45 degrees, the 30, 60, 90 triangle, those are big ones that you need to know. So, all right, so those are our components. Then we add up the components. Remember, Rx is AX plus BX. That's going to be 1.71. And Ry is AY plus BY. That's 0.71 plus 1.7. What's that, 2.4? I'll just call it 2.4. I'm just going to call this 1.7. All right. And then I have those vectors. I can just do the Pythagorean theorem. That's going to be 3.0. And then if I want to know the angle, I use the tan function, or the inverse tangent function of Ry over Rx. That's the opposite over the adjacent. And that works out to be 55 degrees above the x-axis. All right, so those are the steps that you take in adding up vectors. Said on the test, you could just have a straight up vector problem. I give you 2 or 3 vectors, one or more of which is off axis, and you just have to add them up. Hopefully, I know for some of you this isn't sort of knee-jerk, but hopefully it will become knee-jerk reaction to this, that when you see vectors that you just say, oh, I need to find the x and y components, I need to add the x and y components, and then I need to use the Pythagorean theorem and the inverse tan to find the sum of those vectors, because we're going to have to do that a lot as we get into chapter 4 and then into next semester as well. We'll be doing this a lot. Okay, so it needs to be sort of second nature to you. And the only way to do that, of course, is practice. I tell you, I've been learning racquetball. I've been trying to learn how to play racquetball, and I'm not very coordinated. Like, I'm not really athletic, so it's sort of hard. I sort of look like Elaine from Seinfeld when she tried to dance. You ever seen that episode? Y'all don't know Seinfeld, do you? Yeah. So I sort of look like her when she dances. Spastic, I guess. But this guy, I'm meeting with this guy. He's like ancient. He's like 75 or something, Roy Daig. But he plays racquetball, man. He is beautiful playing racquetball. He can just get around the court really quickly, and he knows exactly where the ball is going, and he can hit the ball like 2 inches off the floor, and you have no hope of ever hitting it back to him. But he said that, you know, he's practiced so much that he doesn't even really think about playing. And it's a similar way here that you just need to practice so much with this that you just don't even really need to think about it. That when you sit down and you see a problem, that it just comes second nature to you. And on the exams, it really needs to be that way. It really needs to be second nature to you. Because, you know, the exams are sort of compressed into a short time, and you really need to not spend much time thinking about it. And like we were playing yesterday, and I didn't feel like I was taking a lot of time, but by the time I thought about what I needed to do, it's like the ball was already gone. And the same thing happens here. Like you really need to not have to think about things. You just need to be able to do it. That's true for all of your courses because you're all in difficult courses, right? You're all taking difficult courses, and it really needs to become second nature to you. So you don't even really need to think about it. You just sort of do it. If y'all want to play racquetball, I'm getting a little bit better. We can go play if you want. Okay, let's look at these. I like to make a little table when I add up vectors. I make a table with my x and my y components. I have it drawn out for you here, but usually I just sort of make a table like this. I say x and y, and then I calculate all my x and y components. So, but that's what I have drawn for you here. Um, so here we have these three vectors. Why don't you go ahead and find the x and y components of those vectors? Go ahead, I'll give you a little head start before I jump in. Or find the x and y components. You'll find they're pretty simple numbers. Goodness bless you. Got some of those x and y components yet? For A, maybe? What you got for A, anybody? Y'all still working? All right, I'll give you a second. Zach, do you have A? Okay, the x component is 1. Do you have the y component? 2, right? Do I have B? Anybody else have B? Okay, very good. 3, -4. We'll come back to why that is. C, anybody? All right, yeah, so these are our x and y components. Is everybody able to get at least the first couple of these on your own? Yeah. All right, so here, 1 and 2. This one comes out as 3 and -4. The reason is that vector B is below the positive x-axis. It's always nice to be aware of sort of where your vector is. So if I were to draw the vector B is looks like this. And so it's going to have a y component that is -4 and an x component that is +3. It's 3, 4, 5 triangle, right? Um, so it's negative because it's below the x-axis. It's in that fourth quadrant, so it's going to have a positive x component and a negative y component. We'll see some more questions about that in a little bit. And then vector C, notice that it is above the negative x-axis. So it's like right here, this is vector C. So it has a positive y component and a negative x component. And that is shown here. Now, depending on your calculator may or may not give you the appropriate answer. Some of your calculators are a little smarter than others, and they're able to give you the actual sign for the component, but a lot of yours won't. So, I think the best way here is just to draw out your vector and then say, well, this vector is in the fourth quadrant, so the y component is going to be negative. It's always good to sketch out where your vector is in your coordinate system so you can figure out, what direction it's pointing and then figure out what are the signs of the components. All right, so now that I have my x and my y components, I can find Rx and Ry. Rx is just going to be 1 plus 3 minus 2, just adding up those x components, and Ry is going to be 2 minus 4 plus 5. So that gives me 2, and that gives me 3. And then if I want to find, this is 2 squared plus 3 squared, that's 3.6. And then theta is inverse tan of Rx and Ry. Or excuse me, Ry over Rx. And that turns out to be 56 degrees. I'm going to rewrite these x and y components for these three vectors over here. I want you to try something else. Now, instead of finding a plus b plus c, I want you to find a minus b minus c. So there's the x and y components. They're all still the same, but think about what happens when I subtract a vector. And we did this graphically before. What happened when we subtracted a vector graphically? What did we do to it? Right, we flipped it all the way around the opposite direction. So whenever you have a negative, it becomes a positive, and whenever you have a positive, it becomes a negative. That's true for your components too, that if you have a positive component, it becomes a negative component. If you have a negative component, it becomes positive. All right, so try that a minus b minus c. Think about what that does to the components of particular vectors, and then do the same thing. Please go ahead and find the magnitude of the vector and the direction of the vector. And we'll do a few clicker questions. I get the x component of r now? It's 0, right. So I get 0 here, and the y component is 1. Right, so I have my negative b, this becomes negative 3, and positive 4, and I have negative c, that becomes positive 2, and negative 5. I just negate all the components of those vectors, because if you think about this, before the vector b, let's see, what quadrant was it in? It had a positive x component and a negative y component. So what quadrant does that put it in? 1, 2, 3, or 4? It puts it in the fourth quadrant. This was the vector b. And so the vector negative b is going to be here. So it will have a negative x component right here and a positive y component right here. I just flipped the thing completely, and it changes the sign of the components. Let's see, so what is the magnitude of this vector? It's just going to be 1, right? Square root of 0 squared plus 1 squared is square root of 1, so it's going to be 1. And what's the angle of the vector? Let's draw it, okay, and then you'll see it. So I have a x component that's 0, a y component that is 1 meter long, and so the angle of that vector is 90 degrees. Okay? So if you want to go through this whole process, you can just say the inverse tan of 1 over 0. Oh, will that give you 90 degrees when you put it in? No, that doesn't work. It gives you an error. But you should be able to draw it and just show that it's equal to 90 degrees. All right. Those are pretty straightforward, fairly easy. I want the question on the test to be a give me, okay, that everybody gets it right. Uh, it makes my life a lot easier, like if everybody gets the question right, because then it's just like I go through and I write -0 on all of them. I really like those questions a lot because it saves me a lot of time. Y'all like them too? Yeah. All right, let's try a few clicker questions. I think we left off here. Did we do this one, 3.2a? Yes, we did do it, right? So if I double both components, it does not change. It makes like two similar triangles. A certain vector has x and y components that are equal in magnitude. Which of the following is a possible angle for this vector? And I'll stop at about 40 seconds. I'll go on to 45. Just guess if you're not sure. Oh, awesome. Let's see, did I tell y'all the knock knock joke? I didn't. Knock knock. Interrupting pirate. Oh, I told y'all that one, shoot. Okay, why can you never hear a pterodactyl go to the bathroom? Because the P is silent. That's pretty good. Okay, so 45 degrees, there are actually, a bunch of, or four particular vectors that could fit this bill. This one, this one, this one, or this one. This one would be 45. Uh, this vector would be 135, and on and on. This vector would be 180 plus 45. That's what? 225. And then you get the idea. This vector is 270 plus 45. What's that? 315. All right. Yep. You're adding vectors of length 20 and 40 units. What is the only possible resultant magnitude that you can obtain out of these choices? We did a problem very similar to this before. Think about what's the maximum and the minimum you can get when you add up these vectors. All right, just a few more seconds. I'll stop at 50. Awesome. C is right. Remember, there's a max and a min. The max is if they're both in the same direction. That'll be 60 units. The min is where they're in opposite directions. That's 20 units. So somewhere between 20 and 60. And that C is the right answer. Is the only one between 20 and 60. Okay, we're going to get into this next time. It's projectile motion. Let's do one more quick example. I think I actually had two more examples, but I think we'll just do, no, just do this one. Um, watch this little video. This is just a little French cartoon called Comic Strip. And it's about this little boy that gets invited to a birthday party. A little girl invites him to the birthday party, and he's walking to the birthday party. And just sort of want to think about his path that he takes. and what that path is in vector notation. So let's just watch the little clip. It's kind of a fun clip. But whatever what I'm concerned about is this map that he had. There should be a picture of it in your book. Um, and I want to try to map this out in vector notation, sort of like what y'all did in the lab with the vector scavenger hunt. Did y'all like that little scavenger hunt? Was it kind of fun? You didn't really like it? I guess you could have. Yeah, but that's not nearly as much fun. All right, so anyway, we have this path that he takes. He goes a certain distance in that direction, a certain distance in that direction, like that, and then like that. Now we don't know the cardinal directions exactly, but where he is, but we'll just assume that up is north, down is south, what's that, east, and then west. And so we can describe his vectors. We can draw a vector diagram for this. Might look something like this. Say I have 5 meters south. That would be negative 5 meters, right? Because we take south to be down. Maybe 20 meters east. 20 meters south again, which is going to be negative 20. And then 10 meters east, that'll be positive. And then 5 meters north. And so that set of vectors gets you to your final location. And so we want to add up the x and y components of these. These are pretty easy because they're all on axis, but I want to show you how we express in cardinal directions when we get to the end. Our 5 meters south, x component is 0, negative 5, 20, 0, 0, minus 20. You can fill out the rest there. And then when I get those x and y components, I'm just going to add them all up. What's the next vector? What are the x and y components? 10 and 0, and then 0 and 5, right? So if I just add these up, I get 30. Over here I get, what, negative 20. So I'm going to have a vector that will be 30 meters in the x direction, and then minus 20 meters like that. And the sum of these vectors will be in this direction. Right, notice that if I go back up to the original diagram that I drew, my vector is going to look like this. It'll have that's the vector itself. This is the x component, this is the y component, this is that 30, this is that minus 20. And then I want to find the magnitude and direction of that vector. Let's see, I'll just do it here. I want to find that angle. I'll just call it theta. I say theta is the inverse tan of y over x. That's 20 over 30. And that gives me an angle of 34 degrees. People might do cardinal directions a little bit differently, but typically I would say that this is south of east. South of east. So if I think about my compass rose, right, this direction is east. If I move below that, I'm moving south of east. Y'all express cardinal directions typically like that? Yeah. Whatever. So that's how I do it usually. So south of east. So for example, if I have something like this, what would I call this? North of west, right? Or if I had this, that would be north of east, right? And always measuring the angle from the x-axis, either the positive or the negative x-axis. That's the east-west axis. All right, and then I can also find the magnitude of this. The magnitude is the square root of 20 squared plus 30 squared, which is 36 meters. 36 meters at 34 degrees south of east. Well, hopefully you have a pretty good grasp of this now. There are a couple of homework questions if you need extra practice for it, and you can find some problems on the old exams too. But I would expect a problem, hopefully a simple problem, uh, on the exam. More about that later. All right, folks? Feel comfortable with that? Okay. Let's move on to projectile motion. Next week in lab, you'll be doing a lab on projectile motion, which hopefully that'll help you some on this. Um, Projectile motion, not that hard. Really all you're dealing with are kinematics problems, both of which we've worked already, one of which you have acceleration, one of which you do not. So they're just like the kinematics problems that we've done already. It's in the horizontal direction, or you're going to break it down into horizontal and vertical motion, the motion in the x direction, the motion in the y direction, and we really just have some simple assumptions about both of those. In the horizontal direction, the acceleration will be 0, and as a result of that, you're going to have constant velocity. Right. In the vertical direction, our acceleration, I'm going to start calling this AY. I'll call that AX and this AY. In the vertical direction, our acceleration is going to be minus 10 meters per second squared. So we'll have different velocities, different accelerations uh, in the horizontal and the vertical directions. And basically, we're just going to split those two things up completely. When we deal with a projectile motion problem, we'll work with the motion in the x direction, and we'll work with the motion in the y direction. And while they're related, we'll treat them separately. Just as an aside, an angle of what gives maximum range? Right, we all know this. Like if you're ever trying to squirt somebody with a water hose, you ever tried to squirt somebody with a water hose, and they run away from you, right? You pull up the hose to a certain height or to a certain angle, and if you go too high, it starts coming back towards you. If you go too low, it comes back towards you as well. 45 degrees is the angle that gives you maximum range. That's useful information if you're ever trying to get somebody with a water hose. If you're not sure about that, you can go and try it at home. Just take a water hose and sort of go through all the angles, and you'll find that angle of 45 degrees gives you maximum range. The reason is it gives you maximum hang time. It gives you maximum time in the y direction, and then it also gives you a good x velocity. All right, so if we think about just a simple projectile, an object that starts here and has a velocity that travels like this in this direction. Um, it starts out with a y velocity or a velocity that has a y component and an x component. And remember, the acceleration in the x direction equals 0. The acceleration in the y direction equals minus 10. So what's going to happen to Vx as we go through this motion? It's unchanging, right, because the acceleration is 0. So notice that the length of Vx is always the same. If I were to plot Vx versus t, what would it look like? Would it be a positive slope, a negative slope, or a zero slope line? Zero slope, it's just going to look like that because Vx is always constant. By the way, if I were to plot x versus t, what would that look like? Positive, negative, or zero slope? Would the slope be increasing, decreasing, or staying the same? Bean said it was a positive slope, which is true. Would it be increasing, decreasing, or staying the same, the slope? What, Claire? No, was that you, Sydney? What did you say? No. We're looking at just the x direction. Just the x direction. What happens to the velocity in the x direction? It does what? It's constant, right? So the slope of a v versus t graph, or excuse me, an x versus t graph gives us what? Velocity. So the slope then is going to be increasing, decreasing, or constant. The slope is going to be constant. So my slope here will be positive and it will be constant. That's for the x direction because the slope of this graph gives the velocity, and the velocity is constant, so the slope is constant. All right. Now, on the other hand, my y velocity starts out in this direction. Because it's accelerating in the negative direction, it gets smaller in magnitude. At the top, it goes to 0, and then it begins to increase again in the opposite direction. So if I were to plot Vy versus t, what would it look like? Would it have a positive, negative, or 0 slope, Vy versus t? Positive, negative, or 0 slope. Remember, what does the slope of a v versus t graph give you? Acceleration. So if the acceleration is minus 10, what is the slope of this graph going to be? Positive, negative, or 0? What is it, Lazarus? It's going to be negative, and it's going to start up here, and it's going to go down like that. So this is when the upward ascent, when it's going up and slowing down. This is at the top, and then this is coming down. All right, so that's a graph that we've seen before. All all of these graphs describe this motion, but some of them describe it in the x direction, and some of them describe it in the y direction. By the way, this is the same graph that we had for this motion. When we have something that's just throwing it up, that's that same graph. Okay, so that problem that we worked last chapter will be the same for the projectile motion problems. They get a little more complicated than the ones we did last chapter, but not a whole lot more complicated. You'll see. Once you separate them into the x and y components, it's just like doing chapter 2 stuff, and you'll be fine on it. Now, if I were to plot y versus t, what would this look like? And this is sort of what you would expect it to look like, but not for the right reason. What would this look like, I think? It's gonna be a parabola. Or actually, is it a parabola? Yeah, I guess it is. It's gonna look like that, um, where I have a big slope initially. It goes to 0, and then it goes like this. Right? Okay. This describes the y motion. Like this looks like the path that the object takes in physical space in the xy plane, but this is different. This is the y position versus time. And what this is only describing the y position versus time. Because remember, this graph, it looked the same for this motion that's just moving up and down. You remember this graph from last chapter? Okay. So our projectile motion, we'll just split it into two separate pieces. We'll split it into the x piece and the y piece, and you'll see then that it's pretty easy. Let's see, I have a little video I want to show you. A lot of you did this lab already last week, uh, but in this video, this is a family that lost their home or lost all their home videos in a fire, and so now they're trying to remake those home videos, and they've taken their teenage boys, or God, I mean, I think they're 19, 20 years old, and they're remaking these home videos. So let's watch it. The first little bit's just for fun, but then the second bit is a clip where the guy and his dad are playing basketball, and they're trying to, well, we'll look at the projectile motion of it.